In the last lecture, we met the basic operations of set theory: union, intersection, and complement. In this video, we're going to see how those operations interact with one another. So let's begin with some of the simplest properties of union and intersection, which is the commutative laws. So these statements 1 and 2 are called the commutative laws for intersection and union. When we talk about commutativity, we're talking about the order of something not mattering. So when you swap the order, it doesn't change anything. So the statement here is that if x and y are sets, then first of all, x union y is equal to y union x, and second, x intersect y is equal to y intersect x. So this is the kind of thing which is fairly clear if you draw Venn diagrams of these things. If you were to draw a Venn diagram for the union of x and y, well, here is x and here is y, and it doesn't matter whether you take the union of x and y or the union of y or x. Whatever you do, the result of the union is just everything shaded in. So this seems pretty obvious. So let's think how we might do a proof. We met in our very first lecture about sets a general method for doing proofs of equality of sets, which was the double inclusion method. You prove, in order to show A equals B, that A is contained in B and B is contained in A. And I said that was a general approach you can use all the time. But it's not the only way. I mean, we might, for example, just argue that the definitions of these sets were equivalent to one another. So that's what we'll do here as an alternative. So x union y, by definition, is the set of all things A with the property that A is in x or A is in y. So really, the fact that this is equal to y union x is a property of this logical operation OR. So P or Q is true when one of P or Q is true. And that's the same as Q or P being true. That's also true when one of P or Q is true. So here, this is the same as A in y or A in x, because if you have a statement P which is true or false, then P or Q is true if and only if. I'm writing if with two F's here, that's short for if and only if Q or P is true. If you've ever seen a truth table for OR, you'll notice that it's symmetrical in Q and P. So this last set is actually, by definition, y union x. So this logical argument, the fact that logical OR is symmetrical, P or Q is true if and only if Q or P is true, tells us that x union y and y union x are equal. Their definitions are the same. Of course, exactly the same thing applies to logical and logical and is what defines intersections. X intersect y is the set of all things A such that A is in x and A is in y. And the same observation we made about logical OR applies to logical AND. So once more, if P and Q are things which are true or false, then P and Q is true. If and only if for short, Q and P is true. So this second set, by definition, is y intersect x, and therefore x intersect y and y intersect x are equal to one another. Our next fundamental property of union and intersection is called the associativity property. You might have met associativity properties for other operations like addition or multiplication. So the associativity property for addition is that 1 plus 2 plus 3 is always equal to 1 plus 2 plus 3. And in general, for any three numbers, this property holds. That's called associativity for the operator plus. The next proposition says that union and intersection are also associative. So x union y union z and x union y union z are equal, and similarly for intersections. So I'm not going to give a proof of this one. This is just another proof where it follows straight from the definition, and the fact that the logical operations or and the logical operation and are also have this associativity property. So really the reason I'd like to write down and record this associativity property for unions or intersections is that it allows us to drop brackets. That's the useful thing about this associativity property for operations. It lets us write things like 1 plus 2 plus 3 without any ambiguity about, am I supposed to do 1 plus 2 first and then add 3 to that, or am I supposed to do 2 plus 3 first and then add 1 to that? So similarly, it lets us write A1 union A2 union A3 and so on up to AN without any ambiguity about whether I'm supposed to bracket A1 union A2 first and so on. So associativity is a kind of bracket removal property which is very useful because it allows us to write nice simple expressions like these two without having to put in a bunch of brackets. More interesting is De Morgan's laws for union and intersection. So here we're thinking about two sets x and y which are subsets of a larger set x. And so when I write x complement or y complement or anything else complement, what it means is the set difference of omega with that set. So x complement will be omega take x, and x union y complement means omega set minus x union y. De Morgan's laws tells you how unions and complements interact with each other and how intersections and complements interact with each other. In particular, the first law tells you that the complement of x union y is the intersection of the complements of x and y, and the complement of the intersection of x and y is the union of the complements of x and y. So complement swaps intersection and union. Again, this is the kind of thing you can convince yourself of by drawing a Venn diagram. And I'm going to attempt to do that in the space up here. So I'm going to draw a big box for the set omega, which contains all the sets we're talking about. So this big box is supposed to represent the set omega, of which x and y are subsets. And I'm going to draw my x and y in the most general case, so they overlap a little bit, like this. So here's the x and here's the y. And a good exercise is to actually colour in the region x union y and then work out where the complement of x union y is, and then work out which region of this diagram x complement is and y complement is, and then work out the intersection of the complement of those two complements and convince yourself that those two areas are the same area on that picture. So if you've never done this before, then you should pause the video, draw this yourself and do it, because then you will have convinced yourself of the truth of the first of De Morgan's laws. Okay, I hope you did it. Anyway, let's move on to a proof of, I'm just going to give a proof of one of De Morgan's laws because the other one is similar. And let's talk through the proof which I've written down here, which again, I'm going to do by arguing logically about which things are elements of both of the sets in the first De Morgan's law. So this one. So we'll argue that something lies in the left-hand side if and only if it lies in the right-hand side. In other words, that those two sets have the same elements, so that's the definition of them being equal. So let's look at line 1. An element x belongs to the complement of x union y by definition if x is not in x union y. That's the definition of complement. So let's write down why this is true. So definition of complement. So if x is not in x union y, well, that means it's not in x and it's not in y. So this second if and only if is simply because not being in x union y means that you're not in x and you're not in y. And that's equivalent to being, well, x being not in X is equivalent to X being in X complement. X complement is the set of things which are not in X. So I guess we should begin this proof by talking about elements of omega, just so we're clear about what's going on. Then X being not in X is the same as X being in X complement, and X being not in Y is the same as X being in Y complement. So this third line is simply a rewriting of the second line using the meaning of the complement and the meaning of not being a member. And finally, if you've got something which is not in the complement of X and not in the complement of Y, well, that's true if and only if X is in their intersection, because their intersection is defined to be exactly the things which are in both of them. So we're done. This is a proof of De Morgan's laws. So really there's some kind of logic happening in the background here. If you'd like to read more about that, you can go and look at a logic text that discusses the properties of logical and logical or. A nice one that I like is a book by Martin Liebeck called A Concise Introduction to Pure Mathematics. You'll find that on the suggested reading page for 0007. So let's move on. The final thing I want to say is that we can generalize De Morgan's laws to multiple sets. So if you have a list of as many subsets as you like of a set omega, even infinitely many, then the complement of the union of those sets is equal to the intersection of their complements taken one by one. And the complement of the intersection of those sets is equal to the union of their complements. So this generalizes De Morgan's laws to when you have more than one subset. In fact, even to any finite number of subsets and even to an infinite number of subsets.